Okay, our topic for today is the center of mass. Center of mass is where gravity acts on average. And if you have a uniform object, then the center of mass will just be right at the geometric center. Cm for center of mass. We're going to extend the location of the center of mass to piecewise objects. And for piecewise objects, you find the location of the center of mass using a weighted sum. You take the location of a piece I and multiply by the mass of the piece I, and then normalize by the sum of the masses. You do the same for the y-coordinate. So here is an asymmetric object, and we're going to find the location of the center of mass. And so the first thing to do is to set up an axis. So we'll let this be our x-axis. Then clearly we have one piece here is at the 0 coordinate, another piece here is 8 meters along. So for the x coordinate of the center of mass, we do the weighted sum, mass of piece I, location of piece I, divide by the sum of the masses. So the first mass is 6 kilograms, it's centered at 0. Then we have 2 kilograms centered at 8 meters. And then we divide by the sum of the masses, which is 6 plus 2. This is an answer of 2 meters after you cancel off the eighths and cancel off the kilograms. So the center of mass is located about here. And if you look, you'll see that's really the balance point for the system, because if you've got 6 kilograms 2 meters away and 2 kilograms 6 meters away, then obviously that's going to balance. Next, let's consider this two-dimensional object. So we'll put a y-axis here, and then we'll put our x-axis here. And we need to assign coordinates for the centers of these two objects. So this first piece, we'll ignore the thickness of the piece, and then its x-coordinate will be 0, and its y-coordinate is half L. This piece up here, the x-coordinate is half L, and the y-coordinate is just L. So when you find the x-coordinate of the center of mass, you find, we have to do this algebraically, the first piece is centered at x equals 0, the second piece is centered at L over 2. Then we divide by the sum of the masses, so we get mL over 2 divided by 2m. Now simplify that, cancel the m's, L over 2 is L over 4. Next, for the y-coordinate, we're now going to take the mass m and find the y-coordinates of the two pieces. This one is centered at L over 2. The other one is centered at y equals L. So this is mL over 2 plus mL. That's 3 halves mL. We divide by 2m. So the m's cancel. 3 halves L divided by 2 is 3/4 L. So the y center of mass coordinate is 3/4 L. The x center of mass coordinate is L over 4. So we see the center of mass is located around here, which makes a lot of sense. Center of mass does not have to be located on the object per se. For instance, for a donut, the center of mass will be in the hole in the middle. Okay, here's one for you to try. We want to find out where the location of the center of mass of this object is. Now, in problems such as this, you'll typically be given a coordinate system and asked to answer in terms of that coordinate system. So I'll put this coordinate system down, and I'll ask you, relative to that coordinate system, what is the coordinate of the center of mass? Pause the video, try the problem, and then compare with my answer. Okay, so hopefully the first thing you did is find the location of these 2 points, the centers of those 2 pieces. This is 3 meters long, so this will be at x is 1.5. Here we have to go 3 meters plus another half, so this is centered at 3.5 meters in this coordinate system. Common mistake is to put something like 3 or just even 2 down here, but you've got the full length of this object, 3 meters, and then half of this one. So the center of mass of this compound object, of this piecewise object, you got 10 kilos, 1.5 meters from the origin. Then you have 25 kilos, 3.5 meters from the origin. And then just divide by the weighted sum, or divide by the sum of the two masses, and I get about 2.54 meters. So the center of mass is located somewhere right around here. Now, center of mass is an important concept in physics for several reasons. First of all, when we're doing force analysis, if we're just trying to find the acceleration of the object, we can pretend that all forces act at the center of mass. So for instance, on a car, there'd be weight everywhere on the object. There'd be normal forces from the ground pushing up on two tires, and then there would be frictional forces. Let's see, if we're slowing down with all four wheels, there'd be a friction force at each wheel. So it would look like this. And then, yeah, there'd be gravity everywhere, but we would just take one gravity. So here we'll just draw gravity absolutely everywhere, because every little bit of matter is attracted to the center of the Earth. Those are not great arrows, but you get the idea. Now, it's a great simplification to consider the center of mass, because we say that there is a gravitational force that acts at the center of mass. The normal force, we can pretend it acts at the center of mass, and the friction force too. So for the purpose of finding the acceleration, we could pretend all those forces act at the center of mass, and this is a great simplification. I'm just going to try and make these arrows horizontal and vertical a bit more. So that's one reason why the center of mass is an important concept. Now, of course, when you do that, after you found the acceleration, doing this actually is fine for finding the acceleration, but it is not sufficient for analyzing the full motion of the object. For instance, you miss out on any possible rotation. And we know that if you jam on the brakes in a car, the friction forces on the tires will actually cause it to, the friction forces will actually cause the car to rotate. There's a torque there. I don't know why it's insistent. Oh, there we go. Now maybe it'll let me move it. There we go. So the friction forces which act down here at the road actually create torque about the center of mass. And that's what makes the car nose down a bit when you do a heavy braking, because friction forces create torque about the center of mass. There we go. So there's two torques in this direction around the center of mass, and that causes the car to nose down. Okay, so that's one reason why center of mass is important. Another reason is that if you have a closed system, then the center of mass is going to stay fixed in space or move uniformly. This ends up just being equivalent to the law of conservation of momentum. So the center of mass is intrinsically linked to two discussions of momentum. And we could see that in the following examples. If you fire a gun, then this is a closed, isolated system. The only forces are action-reaction forces in the firing process. The bullet's going to go forwards, and the gun is going to recoil. And the motion of the gun barrel back and the bullet forwards is such that the center of mass location remains fixed, doesn't move, stays right there. Another classic example is putting a cannon inside a rail car and firing it off. Well, the center of mass, because this is a closed system, the center of mass is going to stay fixed. The cannonball is going to go one direction, and the cannon and rail car is going to recoil in the other. But again, the center of mass stays in place, and will do so as long as you have a closed system. Now, here's an interesting example that you can probably only solve easily using the concept of center of mass. If you've ever been in a canoe, you know that if you stand up at the back and walk to the front, that not only do you move, but the canoe moves as well. That's because you're exerting a force on the boat, and that's going to cause it to move backwards in the water. So here we've got a car on a platform. The car is going to drive to the end. Well, the friction force that propels the car forwards is going to push this barge backwards. Let's set up a coordinate system. And it's important that we are a bit careful about this and use the same coordinate system at the beginning and at the end of this motion. So there's our coordinate system. So this is going to be 0. So we'll pretend that the car is a point object, so it starts at 0. This is a 10-meter long ferry. So that means the center of mass of the ferry was originally at 5. Okay, so we know the car is going to drive to the end. It's not going to reach 10, and the ferry is not going to be at 0 at the end. The ferry is going to move back a distance. Well, I guess we could just call it x. Yeah, let's call it x. So this distance here is x, and this distance here is x. So the center of mass of the ferry isn't at 5. It's now at 5 minus x. And the car isn't at 10. It's at 10 minus x. But you see, because this is an isolated system and the only forces are action-reaction forces, the center of mass must stay fixed. So what is the center of mass in this coordinate system? Well, we can calculate it using this first diagram. So it's going to be sum of mixi over sum of mi. So that is a 1,200 kilogram car at 0 and an 18,000 kilogram ferry on average at 5. And we divide that by 1,200 plus 18,000. So that's the location of the center of mass, and it's going to be a little bit this side of 5. The ferry itself would be centered at 5, but the location of the car here is going to drive the center of mass back a little bit. Let's just put a line on there indicating that location. It's probably somewhere about here, and it's not going to move, right? So it's going to be at the same place after the car. Come on. Thank you. Does not want to select that line. That's probably about where it'll be. Okay, so now afterwards, it's got to be the same spot, but now we're going to have a statement in terms of our unknown x, because now we've got the 1,200 kilogram car at 10 minus x, and we've got the 18,000 kilogram ferry at 5 minus x, and then we're dividing by the same 1,200 plus 18,000. And so we can solve this. This just cancels out because it's the same on both sides. Let's see, 5 18s are 90, so it's going to be 90,000 is 1,200 times 10 minus x plus 18,000 times 5 minus x. We can solve that for the value of the variable x, which is how far the ferry moves as a result of the car driving to the end. And so we get 0.63 meters or 63 centimeters. That's how far the ferry is going to move backwards when the car drives to the end. And it's pretty much the only way to solve this question. And so that's our topic for this week, the center of mass. Or rather, their topic for this class.